Okay, so last time we were looking at the fields, and let's finish what we started for the ground state in the interacting theory. Okay, so we had done roughly the following. So if you look at the ground state of the free part of the Hamiltonian, okay, we had expressed as, there's some lag, I don't know why, like this. Okay, okay, and then we had acted upon on both the sides with this operator. Okay, and this gave us the following, because all these states were killed when we took lambda going to infinity limit, keeping epsilon fixed, okay, because they were exponentially suppressed. So this is how we isolated. Now what I will do is I will shift lambda. So this piece is lambda 1 minus epsilon, I epsilon. Now lambda is going to infinity, so even if I add or subtract a finite piece from it, it doesn't matter. So I can make the replacement and replace it by T naught plus lambda 1 minus I epsilon. Okay, because I am taking lambda to be infinity. Okay, so adding a finite piece doesn't matter. Okay, so if I do so, then you can see that I can express ket omega here as the following. This algebra you can check. It will be e to the I e omega T naught plus lambda 1 minus I epsilon, okay, times e to the minus I h T naught plus lambda 1 minus I epsilon. Okay. And if you don't like what I am saying here, that I can shift by T naught, and if you think this is not nice, you can start with a change expression here. So instead of starting with this, you can always have a T naught here itself. Okay, no one can stop you from putting a T naught there, and then you can proceed and you'll get the same things. Okay, so whichever way you prefer, you can do that. Okay, so this constant, there is no operator here, these are some just complex numbers. So I will call this C1 inverse. Okay, so it's some complex number. I call it C1 inverse because I'm going to eventually take it to this side, so that will become C1 times ket omega. So here I call it C1 inverse. This thing, this factor is C1 inverse. And then you have this piece. Okay. So this is C1 inverse, and let me write here times this factor now I'll insert a factor here. I don't think I did that the time we were discussing this, so let me do it now. So I will insert a factor e to the I h naught T naught plus lambda 1 minus I epsilon ket 0. And this I can do because this factor, when acts on the free vacuum, the Hamiltonian h naught has an eigenvalue 0, right? So this will become e to the 0, and e to the 0 is 1. So that's why I'm allowed to do this. Okay, so there is no problem in inserting this operator here. Okay, and if I do this, I can write it as C1 inverse, and let's see what these two operators form. this is forming the following. This is U inverse T naught epsilon. Okay, let's check. So you have IH naught times something here and minus IH. Let's recall what U was. Here. U is e to the IH naught T minus T naught times e to the minus IH T minus T naught. I think I should write it down on the next sheet, on the present sheet. So you see, when you take the inverse of it, the orders will get interchanged and I will become minus I. Note that I am not taking a dagger anymore, because instead of working with real T's, and see earlier H was Hermitian and T's were real, T and T naughts were real, and then taking dagger and in inverse they were same thing, these were unitary. But now, because I am taking time to be complex, we are taking lambda 1 minus I epsilon. Okay, so I have to be careful. Dagger doesn't give you inverse. Okay, because just because e to the I z, if you were to take a dagger of it, you will get e to the minus I z star. Right? I am right now just thinking z of as a z, not as an operator but a complex number. Okay, and this times this will not be 1. Okay, this times this is 1 when z is real, but this times, so the dagger is not the inverse, and what you should do is take inverse, which will just be e to the minus I z. Okay, so that's what we have to take care of. So when you take inverse, the orders will change and the signs will change. Okay, and that's what we have there. Okay, so you see the signs have changed and the order has changed. Maybe I should write down somewhere here U of T naught T is e to the IH naught T minus T naught e to the minus IH T minus T naught. Okay, and with that we see what do you see? Yeah, that this will be the inverse of this. Okay, and then of course your ground state or the free ground state. So that we have, and with this I can write the following. That U inverse T naught minus lambda 1 minus I epsilon acting on free vacuum is this constant C1 times ket omega. Okay, so that's one relation we have found. Okay, and that's useful because U is completely expressed in terms of phi i's. Okay, we have already seen that we can do that. So our goal of expressing omega in terms of free vacuum and phi i's is achieved here, and we were interested in phi i's because phi i's are the things which evolve according to free theory, right? So that's why this is what we wanted to do. And similarly we can look at the bra version of the vacuum and get the following. Let me show that part also explicitly. So what I want to do is, so you take the vacuum in the bra form and again write it in the basis of eigenstates of the full Hamiltonian. Not n prime. Okay, and now you act with this operator, and when you do so on both the sides, you get the following. Okay, same logic as before. So when this operator is acting on ket omega, okay, bra omega, the Hamiltonian here will get the eigenvalue E omega. Remember, H is Hermitian, so it acts on the bra and gets the same eigenvalue as H acting on the ket. So this will give you E omega minus E omega, that gives you 1. E to the 0 is 1. So that's why all the factors have disappeared and you are left with only this piece. Okay, and these ones will give you factors which will vanish when you take lambda to infinity. Okay, so exactly the same argument as before. Keep epsilon to be fixed, take lambda to infinity, you will see you get an exponential suppression. So here you can see minus, minus, plus, okay, so minus, something is not looking good. Let me check. No, sorry. Yeah, sorry, I was thinking wrongly. So for any other state, higher state, this H minus E omega will give you a positive number, right? Because the state will have higher energy than E omega, so that will be a positive number. And then you have minus I times minus I, okay, that becomes a minus 1, so minus epsilon lambda times a positive number, and when you take lambda to infinity, that will give you exponential suppression. So all is good. Now what I will do is, as before, I will insert a factor here which will contain H naught. So what I do is I write the above equation as follows. So this is what I insert here, and because this H naught has an eigenvalue 0 on this bra 0, this exponential gives you really 1 when it acts on the vacuum. So this is allowed, and I should keep my this factor, this one. So this is a complex number here, and then you have bra omega. Okay, and you can check that what you have on the left hand side is the following. So it's again U operator where time runs from T naught to lambda 1 minus epsilon. Okay, if you look at the definition of U that we have, this is what you will get. Okay, and then of course this piece, not this piece, but a piece coming from E omega, so I can write it down. Okay, so that's almost the same as before, and with this I can finally write an equivalent expression to this one, the equivalent of this guy, okay, which relates omega to free vacuum, and the expression is this. So we have bra 0 U of lambda 1 minus I epsilon T naught, okay, and this is equal to some constant C2 times omega, and where C2 is following. Okay, so this is good. So let me quickly summarize where we stand right now. Maybe here. Okay. So I have phi t x as phi I t x, and you have u of t0 t and u inverse t0 t. Okay. Now I am not writing Dagger but writing inverse because of the reason I explained a little time back. Okay, and we have also shown that this operator u t0 t we can express as time ordered exponential. So we have seen that this is minus I t naught to t d tau h I tau. Okay, and then we have further shown just now that u inverse, let me give some space, u inverse lambda 1 minus I epsilon, okay, minus lambda 1 minus I epsilon, this is minus, to t naught, this operator is acting, okay, so this operator acting on ket 0 is C1 ket omega, and the same thing for bra vector is the following. Okay, so this is what we have found till now. Okay, so now we are almost there, a little bit of work is left and we can then have a nice expression at the end. So we said earlier that all that you can ask in quantum field theory can be expressed in following terms. So you can look at these quantities, okay, and that they will answer your most general questions that you can ask if you have knowledge of all these objects. Okay, but now in this course, which is anyway about to finish soon, we will be only interested in quantities that appear when you are studying scatterings. Okay, so when you study scattering, you start from some initial state and look at what's the amplitude that it will evolve into some final state. And when you are looking at those objects, okay, you do not require to know this entire set of inner products that you can construct. Rather, you require a much more restricted set, and they are of this form. Okay, so you require these, and what is this? This time ordering operator just takes this entire product of fields here and orders it according to time, keeping the earliest time to the rightmost, and as you go from right to left, the time increases. Okay, so that's what this time ordering operator is. Now what I will do is I will look at this object. Okay, so for us this is the object that we want to calculate in the interacting theory. Okay, so now let's look at this. So I start with this one. Okay, so I look at time order product of n number of fields which are having their space time arguments as x I1, x I2 and so forth. Okay, and suppose that the times of these space time points are having this relation. So suppose if you choose x1 naught, so out of these xi1, xi2 and so forth, someone will have the maximum time, largest time argument, and that one I am calling the one, that guy is called as x1 and the time component is x10 for that one. Okay, so that's the largest one, and then one of them is x2 and time corresponding to that is the second largest and so forth. Okay, so we have found out which time arguments are largest and how they are ordered. Okay, so now if this is the case, then the above expression I can write with this knowledge as following. Right, so now these are in the right order. So this is the time ordered. So this and this are same because I have taken care of time ordering now. Okay. Now what I do is I use these results which I have here. Okay, and for omega in the bra form and omega in the ket form I will use this, and for the phi's I will use this. Okay, so what do I get? So this guy is equal to, so it will have a C1 inverse, C2 inverse, that those constants will be multiplied here, and then you have free vacuum, this piece, then you have u of lambda 1 minus I epsilon comma T naught. So that's one operator you have here, and then u of x1 I will write in this form, sorry, phi of x1 I will write using this expression. And what is that? It has a factor of u inverse. So u inverse x1, so x1 means I will use x1 naught. So here t will be replaced by x1 naught and the reference time t naught. Okay, and then you have phi I at x1. Okay, then you have u x1 naught t naught. Okay, let's continue further. So for phi x2 I will again make this replacement. So I will have u inverse x2 naught t naught phi I x2, and then you'll have again a factor of u here, I'm not writing, and then you go further, and then you will have at the end phi I xn. There will be a factor of u here, which I am, or rather u inverse here, which I am not writing right now, but I will write the one on the right, and this will be ux n0 t0, and then this last piece, the ket omega. Okay, this will give you u inverse t0 minus lambda 1 minus epsilon ket 0. Okay, so that's what we are going to get. Now you see that this combination is going to appear frequently. U inverse, this one. Here again u inverse, there u inverse, and in between also all these places will have phi's and then u inverse in between. Okay, and also note that when you have u inverse, the first argument is always t naught here. The first argument of both u and u inverse is t naught, and same. Okay, this one is opposite, so we'll worry about it. Okay, good then. So what I'll do is I will define an object V t prime t to be exactly what we are getting there. So we are getting U inverse some t prime, and the first argument is t naught, and then we had a factor of u with again the first argument as t naught, and the second argument was something else, so let's call it t. So that's the definition of V. Okay, and if you check substituting what U inverse is and what U is, you will get the following. Okay, that's one line algebra that you can do. Okay, so check this. Then also check that if you were to take a derivative of V with respect to t, you are going to get h I t V of t t prime. Okay, so that you can do. You already know how things act on U, so this will work out. And of course, from the definition here itself, it's clear that if you take V t prime, that's 1. Okay, because if t prime is same as t, this is 0, this is 0, this is, so there is something wrong, this is t naught. Okay, so sorry, so what I was saying was not correct. So if you put t equal to t prime, this will go away, it will be 0, so this will become 1, this factor, and then you see that these two will just kill each other, these two exponential, and then you get V t prime as 1. Okay, so that will serve as your boundary condition, and you already know how to solve this equation, right? This is the one we solved earlier, where V was written as U earlier. So it will be the same solution because the differential equation is same, the boundary condition is same, so you get the same result. So you are going to get the following. Okay, so now what I can do is I can take this result and substitute in the previous expression. See, these are all V's now. Okay, maybe it will help if I write down that expression here. So what we had was the following. So if you look at omega t phi xi1 phi xin, okay, this we wrote as C2 inverse, C1 inverse, okay, and you can check that this will turn out to be V of lambda 1 minus epsilon x10. Then you have, okay, this is getting difficult. So let me write again. This is equal to C2 inverse, C1 inverse, epsilon x10. Okay, then you have phi I x1. Then you have V of x10, x20, then you have phi I of x2, okay, and you go like this, and then you have phi I of xn, and then V of xn0 minus lambda 1 minus epsilon. Okay, so please verify that this is what you get. So we have combined all the U's and U inverses into these V's. Okay, and also we have already made this clear that x1 has the largest time argument, x2 has the second largest, and so forth, and xn has the smallest time argument. Okay, so this is equal to this one. Now you see that all the operators that appear within this expression, okay, all these operators phi i's and the operators that are present in V, they all are in time order. Let me try to explain that. So here you see the V, the definition of V, or the result for V that we had obtained. Here HI's are operators made out of phi's, or in more general phi's and pi's, but for us it was Phi-4. Okay, and there is a time ordering here. So you remember what was meant by exponential of this? It was, so you have when you are looking at nth order term in the exponential in the expansion of the exponential, it will have n pieces, n factors of h, okay, and you will be integrating over those n h's, but then they are all time order because of this time operator. Okay, so when you look at V of t prime t, the hi factors that appear in that, they all are correctly ordered from lower time to the higher time, going from right to left. Okay, so V t prime t, everything is ordered in time in the correct manner. Okay, they are, I mean, by correct I mean they are ordered, all the fields are ordered in time, with the field at the smallest time appearing to the rightmost and field with highest time argument appearing to the leftmost. Okay, so that is one thing we remember. Now we come to this expression. So let's see this one. This V runs from, you see that this is the lowest time. This is really minus infinity plus some imaginary part, but this is minus infinity, and from there you go to some xn0. Okay, and that xn0 is determined by what field arguments you have chosen here. Okay, so one of them is xn0, which is the least one. So you have here minus infinity to xn0. So all the fields that appear in this factor of V, they will be arranged like this. So you will have hi at minus lambda 1 minus I epsilon, okay, so forth, and then hi of xn0. Okay, so this is how they will be ordered within this V, and this is what we argued here. Okay, then here you have a field which is at xn0, so that is fine, it is correctly ordered. So when you go from here to there, you are still going towards higher time. You continue like this, and the order is never broken, the time order is never broken, as you can see here. When you reach here, for example, the x2, so this field is at time x2 naught, and then all the fields that appear in here, all the hi pieces, hi factors, they are ordered from in the right time order, starting with x2 naught and going towards higher time x1 naught, right? And then you again have x1 naught, so this is also in right time order, and then from x1 naught to infinity, plus infinity. So you see everything is correctly ordered in time within this expression. So what I can do is, I can, instead of having just t's here, okay, I can just use one time ordering operator, okay, and write this. Okay, phi I. Now I will write xi1 0, okay, because now it doesn't matter, right? Once I put t outside, what does it say? It says put everything inside in the right time order. So now I don't have to worry whether this is really the one which is of having the highest time argument, because even if it is not, this operator will reshuffle the fields which appear in here and bring phi I x1 here. Okay, so I can, in fact I should write it even more neatly. I should write it as phi I xi1, phi I xi2, phi I xin, and then we have all these v's which I should keep. So lambda 1 minus I epsilon x1 0, then we have v of x1 0, x2 0, okay, and so forth. Maybe I can write one more, x3 0, x2 0, and then you reach xn 0 minus lambda 1 minus epsilon. Okay, I hope this is not difficult. Maybe let me try to say again in case it is not clear. So if you agree with me that in this expression all the fields, whether they are in V or whether they are explicitly written as phi i's, they all appear in correct time order, right? That's what we argued. Now when I come here, all I am saying is no matter which way you write the v's and phi i's, in what order, this time ordering operator outside will put everything in the right order, right? It will start from the lowest field at the lowest values or lowest time values and go towards field at the highest time values. So the moment t acts on this, it gives you this expression. Okay, so that's why I can just write it in this way. Okay, if you agree with this, then we are in very good shape, because then I can do something. I can look at such products, this one and the next two v's and so forth, and let's see, did I make a mistake? No, I didn't. Okay, so I'm going to utilize some property of V which is easy to check. Oops, what happened? Okay, I know what happened. I will have more sheets. Okay, so here is another exercise that you can check. So show that if you have V of T2, T3 and V of T2, T1, okay, so this argument, the second argument of this factor of this V and the first argument of this V, if they are same, then you get V of T1, T3. Okay, so this will not be difficult to check, and if you use that, then here what will happen, this x1 naught argument will disappear, right? So let's read this. So what it does is this argument disappears, these T2, and you get one V with this argument, first argument, and this argument as the second argument. Okay, I'm sorry, sometimes I'm saying this is the first argument, that's the second argument, but you see, you understand what I'm saying. So what do we get? These two V's will combine to give V of lambda 1 minus epsilon x2 0. Okay, but then you have, so this becomes one V whose this, the rightmost argument will be x1 0, but then you have another V here whose first argument is x2 naught, so that can combine with these two, and then they together will give you, these three will together give you V of lambda 1 minus I epsilon x1 naught, x naught, 1 naught, they disappear, x2 naught disappear, and you get x3 naught. Okay, so if you just run this thing in the chain, you will end up with eventually 1v, because all the v's are going to combine with so you get 1v, where the leftmost argument will be lambda 1 minus I epsilon, and the rightmost argument will be minus lambda 1 minus I epsilon. Okay, so that also you can check. Maybe I can write it as an exercise. So you have v of lambda 1 minus I epsilon x1 0, then you have v of x1 0 x2 0, and then you have v of x2 0 x3 0, and so forth, and you have eventually xn 0 minus lambda 1 minus I epsilon, and show that using this above result that this is just that's kind of obvious, but you can always check. Now we can substitute this result in the previous one. Okay, so what do you get? You get, in fact I can jump one more step. So now I will use this result. See, what is v? T prime, that's just t prime and t appear here. So t prime is the lower limit and the t is the upper limit, and you have this time ordered exponential. Okay, so I can take this and use it for this entire chain of products and substitute in this result. Okay, so what do I get eventually? I get the following: omega. Now there is no gain in writing xi1 xi2. See here, now whatever arguments are appearing here, it's the same arguments appearing here, so I can just stop worrying about those and just write x1 phi of x2 phi of xn. Okay, and what this is equal to free vacuum, one big time ordering operator, and it's not big, it's just the bracket is big, and phi x1 phi x2 phi xn, and then we had our exponential factor. What was that? Exponential of minus I minus lambda 1 minus I epsilon to lambda 1 minus I epsilon d tau h I of tau. Okay. Okay, that's a nice result, except for the fact that I have forgotten C1 inverse, C2 inverse. And also another thing, this should be I. Now everything looks okay. Let me check. Okay, it does look okay. Okay, very good. So this is very nice because all these correlators, okay, these are called, by the way, I forgot to tell you the name. So these are called correlators or Green's functions. Okay, so these objects are called Green functions, and if you have n number of fields, you call n point Green function or n point correlator. So this is the name given to this object, and that object in interacting theory I have expressed completely in terms of quantities that that exist in free theory. Okay, the phi I is evolved with free Hamiltonian, the vacuum is of that of free free theory, HIs also are made out of operators which are phi i's, or in our specific case it's phi I to the 4. Okay, so this is nice, except for this C1 inverse and C2 inverse, everything is good. So what I can do is I can just construct another quantity with which I can get rid of the C1 inverse, C2 inverse. So what I'll do is I'll look at this object, which is just C1 inverse, C2 inverse, and you can check. I think it's I can write it. This is just u of lambda 1 minus epsilon T naught, and then you have u inverse T naught minus lambda 1 minus epsilon. Okay, and this we have just now seen that these combine nicely into one V. This is V. Sorry, that was U. Okay, and you can check that this will C2 inverse. This will combine into, as we have shown above, it will combine into one V. Okay, and then this is again simply C2 inverse, this exponential, there should be a time ordering here. I can just pull out the time ordering, okay, just like in this case, and you have minus I, again minus lambda 1 minus I epsilon to lambda 1 minus I epsilon d tau h I tau. Okay, and then you have, I'm sorry, this is not becoming. Okay, so this is what you get. Now this is with the help of this, if I divide this this green function with this inner product, the C1 inverse, C2 inverse will cancel, and we will have nothing unknown here. Okay, so let me write down this final result that we have got nicely on this one page, and this will be our master formula to work with in the case of interacting theory. Okay, so let me write it. I will call it master formula. Yeah, so here we have So that's our master formula, and now we are in business. Okay, because we can now calculate things because we know how to calculate things in free theory. And here I have expressed everything in terms of quantities which exist in free theory. Okay, so we'll begin from here and start looking at some calculations that we can do in Phi-4 theory. Okay, so see you in the next video.